Welcome to the fifth installment of the Boeing 777 landing gear series. In this chapter, we will discuss the nose landing gear steering system. The nose gear steering is primarily controlled using the steering tillers. The tiller can be rotated to a maximum of 350 degrees in either direction. When the tiller is rotated in the counterclockwise direction, it gives a nose gear left steering command. And when operated in the clockwise direction, it provides the nose gear right steering command. The tiller input operates the bevel gear. The bevel gear changes the angle of rotation and is a part of the reduction gearbox. The gearbox decreases tiller motion and increases the tiller input torque. A torque shaft connected to the gearbox operates the cable drums. The upper cable loop connects the captain's tiller to the first officer's tiller. Therefore, when a command is given using any one tiller, the cable movement simultaneously operates the other tiller mechanism and indicates to the other pilot. The upper cable loop can also be moved using the rudder pedals. The pedals are connected to two different mechanisms: the main landing gear brake pedal mechanism and the flight control rudder pedal mechanism. When the top of the pedal is pressed down, it operates the brake pedal mechanism. The brake control cables operate the brake metering valves, and the main landing gear brakes are applied. When the lower part of the pedal is pushed forward, it operates the rudder pedal mechanism. Left pedal force will operate the position transducers to give a left rudder signal to the flight control computer. The right pedal force will operate the position transducers to generate a right rudder signal. The rudder pedal mechanism will also provide a nose gear steering command on the ground. The pedal is connected to the steering cable via the rudder interconnect mechanism. The interconnect mechanism is mechanically linked to the jack shaft on the first officer's side. A left pedal force operates the mechanism to give a left steering command, and a right pedal force gives a right steering command. The rudder interconnect mechanism holds the steering tiller in the neutral position, whereas the feel and centering mechanism holds the rudder pedals. The feel and centering mechanism spring force is greater than that of the interconnect mechanism. Now let's see how the mechanisms interact when different steering input is given. When the rudder pedal is applied, work is done against the spring force of the feel and centering mechanism. The interconnect mechanism operates the upper cable loop. Steering cable movement will also operate the tiller. When pedal force is removed, the feel and centering spring will return the pedals to neutral. The steering tiller input moves the upper cable loop, and work is done against the interconnect mechanism's spring force. This prevents the rudder pedal from moving when the tiller command is given. When the tiller force is released, the interconnect mechanism spring returns the tiller to the neutral position. Let's look at the interconnect mechanism in detail. The interconnect mechanism has a rudder pedal arm, two free arm assemblies with rollers, the centering spring that connects both the free arms, and the cable quadrant arm that connects to the steering cable. All the arms are installed on the same pivot point. When a left steering command is given with the pedals, the rudder pedal arm will act on the roller and move the number 2 free arm. The number 2 free arm movement will add tension to the centering spring and pull the number 1 free arm. As the number 1 free arm moves, its roller drives the cable quadrant arm. As a result, the steering cable is operated to give a left steering command. When released, the feel and centering mechanism spring force will return the interconnect mechanism and steering cable to neutral. For a right pedal command, the mechanism moves in the opposite direction and operates the steering cable to turn the nose wheel right. When the tiller left command is given, the cable drum moves the upper cable loop. The steering cable will move the cable quadrant arm. The quadrant arm will act on the roller and move the number 2 free arm. The number 2 free arm will add tension to the centering spring, but the pull force on the centering spring cannot overcome the feel and centering spring force. As a result, the number 1 free arm and rudder pedal arm remain stationary, and the centering spring extends. When the tiller is released, the centering spring force returns the number 2 free arm. This moves the cable quadrant arm, the steering cable, and the tiller back to the neutral position. The right tiller commands the mechanism to work similarly, but in the opposite direction. The upper cable loop runs below the flight deck and into the avionics compartment. With the help of pulleys, the loop operates the broken cable compensator. A shaft from the compensator extends into the nose wheel well. The pivot link connects the shaft to a cable drum. The cable drum controls the lower cable loop. The upper cable loop movement in either direction will operate the drum, adding tension to the lower cable loop. The lower cable loop runs through the summing mechanism and winds around the steering collar. The summing mechanism has pulleys for the lower cable loop and a summing lever that is free to rotate on its pivot axis. When a steering command is given, it increases tension on one side of the cable, which causes the summing lever to move away from its neutral position. From the summing lever, an input rod is connected to the nose gear steering valve. Before we understand the valve function, let's look at the hydraulic connection. The aircraft has 3 independent hydraulic systems. The center hydraulic system powers the nose gear steering. The steering valve has 3 input and 2 output connections. When there is no steering command, the output ports are connected to the return line of the hydraulic system, and the pressure line remains closed. When a left steer command is given, the summing lever input rod operates the steering valve and connects the pressure line to one of the output lines. The applied pressure reaches the swivel valves. Each swivel valve has 3 input ports. The swivel valves are above the steering actuators. The rod ends of the actuators are attached to the steering collar. Each swivel valve has 2 output lines. One connects to the rod end of the actuator and the other to the head end. As a result, one actuator extends to push the steering collar and the other retracts to pull the collar. The return line connection allows the hydraulic fluid to return to the center system when the actuator rod moves. As the steering collar turns, the reaction will cause the actuators to move on their pivot. This will also operate the internals of the swivel valve. When the steering collar reaches approximately 30 degrees of rotation, the retract actuator reaches its maximum travel. At the same time, the retract actuator crosses its over-center position. Now the right swivel valve sends pressure to both sides of its actuator. The head end has a bigger surface area compared to the rod end. Therefore, for the same pressure applied, the difference in surface area causes the actuator to extend. Now both actuators extend to turn the collar further. As the steering collar rotates, it simultaneously operates the lower cable loop to release the tension. When the collar reaches the commanded position, it returns the summing lever to neutral and closes the steering valve. The valve releases the applied hydraulic pressure. The steering collar will remain in this position as long as the tiller force is held and the upper cable loop is under tension. When the tiller force is released, the interconnect mechanism centering spring will move the upper cable loop and the tiller to neutral. This will move the lower cable loop drum and add tension in the opposite direction. The cable movement operates the summing lever and activates the steering valve. Pressure reaches the swivel valves. The left swivel valve retracts its connected actuator. The steering collar starts to rotate back to its neutral position. The actuator connected to the right swivel valve remains inactive until the steering collar crosses the over-center position. Now the actuator head end is connected to the pressure line and extends to turn the collar. As the collar reaches the neutral position, the lower loop tension is released, and the summing lever closes the steering valve. The right steering command function is similar. Only the swivel valves and actuators roles are reversed to achieve the collar rotation to the right. The steering tiller input operates the steering valve, and the pressure is sent to the swivel valves. One actuator extends, and the other retracts until the over-center position, after which both actuators extend. As the collar reaches the commanded position, the cable tension is released, and the summing lever closes the steering valve. When the tiller force is released, an opposite tension is created on the lower cable loop. The valves operate to retract one actuator, and when the over-center position is reached, the other actuator extends to return the collar to the neutral position. Now let's see how the collar rotation results in nosewheel steering. The steering collar is trunnion mounted on the shock strut outer cylinder and is between the 2 steering plates that hold the actuators. The collar is connected to the upper torsion link. The lower torsion link is attached to the shock strut inner cylinder. The wheels are installed on the inner strut axle. When a steering command is given, the collar rotation steers the nose wheel via the torsion links. A full tiller left command results in 70-degree nose wheel movement to the left. When released, the nose wheel returns. Likewise, a full tiller right command will steer the nose wheel 70 degrees to the right. The degree of nose wheel movement directly depends on the tension generated on the cable loop. For a given tiller position, a proportional cable tension is generated. The summing lever operates the steering valve, and the nose wheel turns. The steering collar movement neutralizes the cable tension, and the nose wheel holds the commanded position. When released, the wheels return. When the rudder pedals are used for steering, application of the full left pedal command generates enough tension on the cable to steer the nose wheel to a maximum of 7 degrees left. Full right pedal application will steer the nose wheel 7 degrees to the right. The rudder interconnect mechanism reduces the workload during the critical runway phase of the flight. When the aircraft is taxiing, the pilot will control the tiller for steering, the thrust lever for movement, and the pedals for braking. The aircraft has to make sharp turns on the taxiway, therefore the tiller is used. As the aircraft enters the runway, the pilot will switch to the rudder pedals for steering. But the rudder is an aerodynamic surface and needs an airspeed of 60 knots to effectively steer the aircraft. This is where the rudder interconnect mechanism comes into play. The pilot can set the takeoff thrust and focus on the control column. Since the aircraft only requires minor directional adjustments on the runway, it can be easily done using the rudder interconnect nose wheel steering. Once the airspeed reaches 60 knots, the rudder becomes effective and will provide directional control if required. Join us in the next part of the series, where we will discuss the main landing gear steering system. Thanks for watching.